Supplemental math videos from Circle Christian School.
Comparison functions, rate of change. All right, these kind of functions are total basic linear functions. We compare a lot of things in today's world. The comparisons help us to decipher a norm or a constant. It takes the guesswork out of what may happen next. That is, a statistic. This comparison can be shown as an equation or a function. Put something in, get something out. Ratios and variations are kind of a cause and effect type of function. Thus, you put something in, you're going to get something out. You had a cause, you had an effect. Ratios can be shown as comparison in one of these three different ways. And because eventually it turns into a fraction, generally all fractions must be reduced, or in its lowest terms. Remember, your calculator can do that for you, but the best thing to do is just get really good with your multiplication facts. Those are the things that help you reduce and add and subtract fractions and things like that. If you're not good at fractions, get good at fractions. It'll just save your life. And if you're not good, teach somebody else how to do the fractions. It'll help you too. Basic ratio comparison. There's a ratio of girls to boys in a certain class of 3 to 5. If there's a total of 32 students in the class, how many girls are there? All right, generally when they talk about these things, whatever is coming first here is going to relate or be relative to the first thing in the ratio, and boys will be to the 5 because it's the second thing. One thing that happens with most type of ratios when you get this comparison type of thing, the best way to deal with it is just to give it a variable. The thing about these is that they are somewhat two-step. That means you got to go find x, but then you got to go put things back in to find out what the real answer is. So we have 3x and 5x equals the 32 here, which gives us an 8x equals the 32. So x is going to equal 4. Now believe me, one of those A, B, C, or D's is going to be 4. So you have to make sure that you answer the question. And like all word problems, you pretty much want to deconstruct it to a point where you understand this part goes with this part, and this is what we want to answer. So how many girls are there? That means we need to take that 4, put it back inside the ratio here. Oops. And we have 12 girls. And you can always check that out by putting the other inside there, which would give you 20, and you add the two together and go, hey! Yes, it does equal 32. Sometimes we get ratios that are somewhat transitive. That means we got to kind of go through a middle guy here. So for instance, A is to B is B is to C, then A is to C if and only if the B's inside here are the same. However, we have times where they're not the same. You might get a question like, if the ratio of A to B is 3 to 5, so as a fraction, it's like 3 to 5, and the ratio of B to C is like 2 to 7, so we get a fraction like 2 to 7, we actually have to find the least common multiple between the B's, which end up being 5 and 2. So therefore, we end up with a least common multiple of 10. Now, changing these fractions to being equivalent to what it takes to have a 10 here, and I'm going to multiply these by 2, which is going to give me a 6 to 10. And I have to multiply this by 5 so that our B's have a least common multiple, and we get a 10 to 35. So therefore, our ratio of A to C, okay, so again, we can look at this as A to B, B to C, and we need from A to C, our ratio is going to be 6 to 35. I didn't explain it very well in the classroom, but I hope this helps. A type of these ratio functions is called a direct variation. There is this definite cause and effect where you have a k that is a constant variable. Now this is what looks very linear, that y equals mx plus b. We're talking about this part here where the m is basically a k. It's a scale factor. It's a rate of change. That's what a slope is. It's a rate of change that constantly happens with that equation. An equation is a function. Put something in, get something out. My pen's not playing happy. In fact, it's being kind of slow. Oh, I think I was pushing a button on it. That might make a difference. Okay. So ways that you might see this type of problem is words like varies directly, varies equivalently, or directly proportional. So therefore, basically what you're going to do is sometimes you got to go find the k, you got to go find the rate of change, you got to go find the slope of an equation. And the way we're going to do this is we're going to get the k by itself. So k is going to equal y over x. Okay, so we just divided an x out of here and then x out of here. If y equals kx, where k is a constant and y is 27, when x is 18, what is the value of y when x is 30? And you're going, what? It's a word problem, guys. In fact, it's one of the better types of these word problems because they can get a little scientific in here. And what I like about this is that it has basic numbers. So go piece by piece. First thing to recognize is that you've got a direct variation, that you've got a k, something constant inside here. And then it tells you k is constant and y is 27 and x is 18. What is the value of y when x is 30? So you're going to have to find a k value, a constant thing, because you have a new input. What would be your output? And you've got to figure out what kind of direct or constant variation you have between the two. So that's what we're going to do. We're just going to go find k. So we have 27 equals 18 and a k. You divide by the 18, you divide by the 18. And so k is going to end up being 3 over 2. There's your scale factor. There's your slope. That's a terrible 3. There's your scale factor. There's your function. So basically you end up with y equals, my bad, 3 over 2. I went to write a k. And then x. And then you can plug things in all day long and get something out. Put something in, get something out. You have a function. This particular function is linear. Direct variations are linear. Okay, so if 28 pennies weighs 42 grams, what's the weight of grams in pennies? Now there's actually two ways to go into this, but I'm going to do this as a direct variation because there's obviously something directly affecting the other. So we look at this as the x and we look at this as the y. And then if we put this x in, what y are we going to get out? So using our formula of y equals k times x, our y is 42. We want to find our constant and 28. going to divide by the 28. And so therefore K is going to equal 42 over 28, or 3 over 2. Okay, there's our scale factor. Here's our rate of change. And in money, you know, that is kind of rate of change, conversion happening here. So putting it back in, that if I have 50 pennies times the 3 over 2, the K here, what would we get out? And you get 75. All right, now in class, we were actually able to do this as a cross multiplication, that 28 pennies to 42 grams equals 50 pennies to how many grams? Definitely. And I want you to notice this, because when I get to the inverse variation here, you're going to see something a little bit different. But fraction equals fraction, scale factor, okay, kind of that y over x thing, scale factor, slope thing, that you have division problems. Okay, inverse variation, that you'll see words like inversely, inversely proportional, that there is a scale factor here that's on the decrease type of thing. To have the K here, we're going to multiply this by an X and multiply this by an X. So K equals X times Y to find that scale factor here. All right, so 4 workers can build a house in 9 days. Here's my X, there's my Y. 3 workers, days to build the same house. So there's the Y. And so I'm going to put it back in as a scale factor type of thing. I have 4 workers. K over the 4 equals the Y, 9 days. So 9 over 1. And so we get K equals 36. And putting it back into the original equation to see how many days is going to come out when you put a 3 inside there. K is 36 over the 3. So Y is going to equal 12. So 12 days. Now, another way to look at this would be that you have 3 times so many days equals 4 times the 9 days. And notice how this actually resembles the K equals XY thing here, where up here we had these fractions and division problems. Here we have a multiplication problem. Not to be too confusing in here, just realize that K is some sort of scale factor. It is a constant. It is a slope. It is a rate of change. And again, there's a function. Put something in, get something out. Okay, last one for this section here. This is actually kind of a 2-part slide that could actually be separated into 2, but generally because I assign these 2 lessons together, I'm actually going to keep the video together. So this is the rest of 4.2. Coordinate plane segment ratios. So what we have here is we have a ratio between 2 points and another ratio between 2 other points, or that is A to P has a direct rate relationship to P to B as a ratio. We can also write it, it's sometimes a little bit better to look at it as R is to S. And the big thing that happens inside this one, they want to know things about coordinate planes, planes? Do you understand coordinate planes? And I'm now going to mix it with things like ratios, rates, slope of change, and here we are back to a function again. What are the coordinates of point P in an XY plane? So I'm in a coordinate plane, and coordinates mean I'm going to have X and Y's whose endpoints are, so A over here is -1 and 4, and B is 4, -6. Even though it doesn't look like it, but doesn't really matter. Nothing's ever to scale inside of an SAT or an ACT anyway. If you really wanted to draw it, they're just going to give you, hey, we got a line, got a ratio going on. Here's what's going to happen. That this segment inside here has a ratio of 2 to 3. That is 2 to 3. That is right here, 2 to 3. And what we have to do is find out, where's P hanging out at? Now, personally, I think this is probably one of the harder things to remember is as a formula type of thing. So I'm just exposing you to it so you can kind of see it, recognize it, maybe make a really good educated guess inside here. But what happens is we're going to find the difference of the x's and the difference of the y's, and that's going to dictate what we add to A to get us to P. So other things to remember is that when reading a graph, initial things happen going left and then to right. Terminating's in the right. Now, where this makes a little bit of a difference is in particular when you get up into pre-cal and some function and things that as you work with some formulas inside there, especially some trig things. Initial starts on the left and terminating's on the right. And when you put the two together in a division thing, it's terminating, take away, initial, which will make a difference in the signs. So that's what I have here, terminating to the initial. So 4 take away the -1 gives us a 5. Going to times that by what's happening with the ratio. So we have an R and an R plus an S. And our result is 2. Same thing that happens with the rise, or that is the y's. This is the difference of the x's. This is the difference of the y's. We end up with these two numbers here. We add them. So therefore, point P is going to give us a 1 and a 0. So A is our answer. Okay, now for the second part of the video, 4.3. Just a quick thought here and reminder that simple probability, that is the favorable outcome over the total possible outcomes, is also a type of ratio. It's written as a probability of an event. So the P just means probability. The E means an event, something that is given inside here. That the ratio that comes out of this is you want favorable out of total outcome. So for instance, let's say we have some yellow marbles. We have red marbles. Yeah, okay, let's say we have 3 yellow marbles and 5 red marbles. What's the possibility of pulling out a yellow marble? Well, the ratio that's going to happen here is that we have 3 yellows. Total outcome of pulling any marble out is going to be the 2 together. So we have a 3 out of 8 chance of getting a yellow marble when we pull things out. And that's just basic, simple probability here. So you'll see that as a fraction also. All right, 4.3. Rate. Unit comparisons. Per, of, part of. Kind of takes us back to a little bit of percent, but a lot of these are going to be different types of mixture, motion type of problems. Different type of rates that you might see is dollars to maybe ounces or pounds. Distance to time equals rate or speed, or another way to look at that is your basic distance equation. Rate times time equals distance. Other ones might be feet per second. So you'll see measurement to time. Trying to think of a few others. Miles per hour. So there's kind of 2 different units being measured or compared here. So taking our first one here, like the motion of something, that John rode his bike to town at a rate of 15 miles per hour. He left the bike in town for some minor repairs, walked home along the same route at a rate of 3 miles per hour, excluding the time that John spent taking the bike into the repair shop. The trip took 3 hours. How many hours did John take to walk back? All right, motion again. So this is where a picture is kind of 1,000 words. Here's old John riding his bike into town to the repair shop, and then here's old John walking back. So obviously the distance inside here is going to be the same going and coming back. It took him 3 hours altogether. We need to know how long it takes to go and walk back. So making a chart is one of the things that actually really help in here, that you're going to break up what's pretty much happening. He went into town, he came out of town, since we got miles per hour, we've got rate, we got time, we get that it equals the distance here, that his going into town took him 15 miles per hour, but you know, we don't really know how many hours. So since the distance is the same here, we know it was 15x. Going out of town took, he was at 3 miles per hour. And time here, you got to think a little bit about this. This is where that mixture thing's going to happen, just a little bit here. That altogether, we had 3 hours. But part of the 3 hours was going in, the other part's the leftover. So the leftover here is going to get represented as the 3 minus x, the leftover. 3 hours take away what it took to come in. And then if we put this together, we have 3 and 3 minus x. Okay, since distance here basically equals distance, or that is, the distance is the same, that's how we're going to set up our problem. And then we play with the algebra. Sometimes what you have to do is just kind of match this up with different examples to see how it will help you also set up inside here. Plus 3x, that's a terrible plus. So we get 18x equals the 9. So therefore, x is going to equal 1/2. But believe me, one of the A, B, C, D's is going to be 1/2. Did we answer the question? No, we wanted to know how long it was to walk back. So that means we're actually going to have to put that into our time here. That to go to town was a ½ hour. So therefore, to walk back took him 2½ hours. I think I would rather ride the bike. Work rate always equals one job. A part of what somebody can do or a machine plus the other part of what somebody or a machine could do to equal the one job, where T, or the variable here, is generally going to be the time, because we usually want to find out what the time is. So part of time always equals one job. So for instance, if one person can paint a room in 3 hours, to do 1 hour would be 1/3. While the other person is able to paint the room in 4 hours, his time would be just 1/4 of the time. So we have a printing press that one printing press takes half as long as the old one. So this is going to be 1/T, and the new one's going to be over half the time. Okay, so generally this new one here is a very strange fraction, or what we call a complex fraction. So what I'm going to do is actually multiply this by 2/1 so I can get rid of this ugly fraction under here, which means I have to do that up top here. So in rewriting this, we get 1/T plus 2/T is going to equal one job. I'm going to multiply everybody by a t because I'm going to ditch the demon. Don't like that t down there. And that's going to give me a 1 plus a 2 equals t. So t is going to equal 3. So working together to print 5,000 flyers is going to take me 3 hours. A few of these were just fun. Map ones and scale factors. Nice, easy ones to think about. But drawing a picture is what helps. So I'm going to show 1.5 inches here equals 120 miles. Oops, it's supposed to be an M. Okay, so if we got 1 foot apart, remember to put your conversions. Convert to same values. So that's the tip there. You may have a foot here, but we're talking inches. So instead of talking a foot, let's talk 12 inches. And how many 1.5 inches are in 12 inches? Well, there's 8 of them. So therefore, if there were 8, we're going to multiply that by 120. And that's going to give us our 960. I like that one. That was fun. Drawing a picture, convert to same values. Okay, got machines. One machine does so much, another machine does another much. How many minutes will it take these guys working together? Well, we started off with hours, so we're going to have to put everything into minutes. So our first one does 360 out of the 60 minutes, and the other one does 140 out of the 60 minutes. And that's going to equal 700 packages that we want done, our one job done. I'm going to simplify this out, and so we end up with a 6x and we end up with a 7/3x, and that equals 700. All right, all you guys that hate fractions are probably going, oh my gosh, fractions. Well, if one of them's a fraction, make them all fractions. And then ditch that demon. Get rid of that denominator. So I'm going to tell you a little bit of math that's happening here. I'm going to ditch my denominator. And I have a 1, a 3, a 1. So our common denominator is going to be 3. So I'm just going to multiply everybody by a 3. And that's going to change it from being a fraction equation to being a basic linear equation here. So starting with the first one here, we get 18x plus the 3's cancel out because this is 3/1, fraction times a fraction. So that gives us a 7x equals the 2100. We had 25x equals the 2100. Let's divide by the 25. And x will equal, handy dandy calculator, or whatever way you want to do it, 84. Take you 84 minutes. Okay, just to let you know that before this one, there's a real cool plumber one that, in all honesty, I didn't do mathematically at all. I just became the plumbers. I went to the job, and I worked it that way. And that's how I got the answer. So see if you can try to do that too at the same time. All right. So let's talk about Joseph, and he typed a 120-word essay, 25 minutes with an average of 240 words on a page. At this rate, how many 240-word pages can he type in 1 hour? This is going to go along a little bit with the plumber. Become the person, type the page, figure out what's happening here. So if he can do 1,200, I probably said that wrong earlier, in 25 minutes, and he has 240 words on a page, then what we're going to do is figure out how many pages are happening here, and that's going to equal 5 pages, which happened in the 25 minutes. Now I'm going to figure out how many 25 minutes are happening in an hour. So if I could do 5 pages in 25 minutes here, then how many pages are we going to do in 60 minutes? Okay, so this is going to be a cross multiplication. We got 25x equals the 300, and x is going to equal 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 12. That it does.
So just pretend you're the person typing the pages. Really, really helps. All right, guys. Little bit by little bit. You may not get the right answer every time, but it's more about the approach here. Practice good skills of deconstruction, breaking things up, drawing pictures, doing some labeling, seeing what they're asking for, those kind of things. And if you get the right answer, hallelujah.